Okay, danke schön. Danke für die Einleitung. Und ja, gut, dass ich es geschafft habe, durch den Verkehr zu kommen in Hamburg. Wie gesagt, wir sprechen heute über Container Image Signing. Interessanterweise natürlich, und das ist jetzt kein sehr origineller Gedanke. Oh, ich muss fragen, Englisch, oder? Okay. Switch to English, no problem. So it's not a very original thought, but obviously our ancestors have been using signatures as a way to identify documents, authenticate documents, and protect its contents since the early ages. They invented different things to do that, from these kind of clay impressions to the handwritten signature, of course, which came up in the medieval times. And they also like to use ribbons and wax seals to certify the authenticity of documents and also to protect the documents from being tampered with. So this was kind of very popular, sealing an envelope with a wax seal. It's kind of the minimal viable product or the predecessor to maybe cryptographic hashing function that we do today to verify the content and to protect it from being tampered with. So yeah, so these signatures were always used to certify the authenticity of documents, identify the origin of the content and the author, and also to protect it from being tampered with. So some well-known problems that we still have today. Which brings us to the topic of container image signing. To start with, I show you two numbers. So this is the year 2015. And in 2015, the first solution for container image signing was actually released, which was part of the Docker ecosystem called Docker Content Trust. And the next number is 2022. This was the year when the Kubernetes project started to sign their own official container image releases. So quite a bit of time has passed. You wonder what happened in the 7 years. Well, not much happened for container image signing for sure. There was the shift from Docker to Kubernetes, and then Docker being dropped as the container runtime for Kubernetes. That didn't help as well, because that kind of sealed the fate of the wide adoption of the Docker Content Trust. So if you Googled a few years ago to check how do I do image signature verification in Kubernetes, you wouldn't find a lot of helpful results. And actually, even if you came up with a solution to do it, it would also be kind of pointless, because you would hardly find any software vendor or open source project that signed their own images. So kind of pointless to even implement it. But of course, this has changed. And so why is image signing now slowly moving into focus? The first reason is that we see a rise of supply chain attacks. And this, of course, raises the sensitivity for this topic. And as part of that, we also see that this idea of signing software artifacts is also coming more into the focus, and is recommended and required by many security frameworks and regulations. So these are kind of the reasons why we see more focus on image signing right now. So let's first look at the supply chain cyber threats. So here's one study from Gartner that predicts that 45% of organizations will have experienced this kind of attack, which is a threefold increase from 2021. And of course, just reading the newspaper, we have witnessed a number of quite famous and widespread attacks, which in parts had catastrophic impact or potentially catastrophic impact. So what are these attacks that are typically categorized under supply chain threats? So one of them was the SolarWinds attacks. So what happened there? So the attackers injected malicious code into the SolarWinds Orion product, and this malicious code was then distributed to all the customers via a normal software update. And this in turn then allowed the attackers to compromise the systems and networks of these customers by exploiting the backdoor that they had put into the code. Another example is log4shell. So this was a zero-day vulnerability, not a backdoor, which was discovered in a popular Java logging library. And this had also widespread consequences because it was this library was used in basically all Java enterprise applications. And it also had quite drastic consequences because it allowed an attacker to run arbitrary code on the system. And then the most recent example, which we could also categorize as a supply chain threat, is the XC backdoor. So this was just this year, where in a quite elaborate scheme, and yet unknown organization injected a backdoor in the XC package during the package build phase. And it was only through pure luck that it was discovered by a Microsoft engineer who wondered why his SSH logins took 50 milliseconds longer than usual. And this was kind of the famous story why this was discovered. But if it wouldn't have been discovered that early, this would basically open up millions of Linux servers to the attackers. So another reason many IT organizations now think about image signing is requirements from a compliance and regulatory source. So we have a couple of cybersecurity frameworks, standards and regulations that prescribe the use of signing software artifacts. And that obviously also includes container images. So just to name a few examples, we have the European Union NS2 directive. This comes into effect this year, and there's a focus in this directive on the supply chain security, and that obviously also means that all the IT organizations that are subject of this directive or of the national laws, they need to implement the best practices to secure the software supply chain. Another example is the NIST cybersecurity framework for North America. There was also an update published in this year, and this also puts a new focus on the software supply chain risk management. And then finally, one example from a framework. So this is SALSA. Some of you might have already heard about it. This is a framework that was originally designed by Google to enhance the software supply chain and to protect the software from typical supply chain risks. And this is quickly now becoming a standard for software vendors and everyone who publishes software to implement these best practices. So what is the goal of container image signing? Yeah, so in a simple sentence, it's really the need of securing the software supply chain for our application containers running on Kubernetes. And more specifically, we want to use this to authenticate the origin, the source of the image, and ensure that they come from a source that we trust. We also want to prevent that in the course of the lifecycle of the software delivery lifecycle, the image is tampered with, and maybe someone, man in the middle, injects some malicious code into the image. And also, this is also used to establish accountability and transparency throughout the software delivery process by attaching signatures and verifying the signatures on the image. So what is this from a technical point of view, this process of image signing? So it means that we add a digital signature to a container image, And we can then use this signature to verify the origin and the integrity of the image and the software that it contains. So by verifying the signature, we can establish who is the source or the author of the image. So this is sometimes also called build provenance. And we can also verify the integrity, as I said before. So the image has not been tampered with while being shipped to the deployment environment. There's basically two signing methods. So one is the private public key pair signing. So you might know this from applications like GPG, from email encryption. And the second one is using a certificate, a code signing certificate from a trusted certificate authority. So let's look at the private public key pair signing process. So the idea here is that you use, that you create a hash from the container image, and then you encrypt this hash with a private key. And the result of that is basically the image signature. And then to verify that, you kind of do the same thing again. So you use the image that you have a signature for. You create again the hash, and then you compare this hash, you decrypted the image signature with a public key, and then you compare the two hashes, and when they match, then you have basically proven that the signature belongs to the image. So the process seems kind of easy or straightforward. But the devil lies in the details, and one of the details is really around the whole public key management. So this has proven to be not really trivial to implement in a secure way. I know many people who started using private public key for email encryption, and then after a few weeks they stopped doing it because it was just too much headaches. And here is no different, right? So obviously, we need some help to do it. We need some technology, some tools to help us do it in a safe way and in an easy way. So let's have a look at the available tools to do image signing. I already mentioned before Docker Content Trust. This is still around. It's one of the oldest available signing tools for container images, available since 2015. It uses a component called Notary to establish the trust and also to store, for example, the public keys and distribute the public keys. I believe the Notary server actually also holds the signature, but I haven't been able to really find this out. Docker Content Trust is heavily integrated in the Docker ecosystem. So if you use the Docker command line, there's a command for that, Docker Trust, which allows you basically to do all the different things around signing and verifying image signatures. The problem with Docker Content Trust, as I already laid out before, is it was never really widely adopted in the Kubernetes ecosystem. And since Docker stopped being the container runtime for Kubernetes, it was kind of not really possible to use it with Kubernetes. So here comes another player, which is the Sigstore cosign project. This has been GA'd in 2021, so it's a relatively young project. And it aims to provide a simple and efficient way to implement signing and verification of container images. There's a few differences compared to Docker Content Trust. So one important difference is that it uses the OCI registry, so your container image registry, to store and distribute the signatures. So this means you don't need to run an extra component, an extra service to do that. You can just use the same OCI registry that also stores the images itself. So that's an improvement. It also provides a public auditable record of image signing events. It's called the record transparency log. So this is not necessarily required to implement image signature verification, but it's a part of supply chain security best practices to have this kind of transparency and to make all the signing events basically audible. One big advantage of Sigstore cosign is that it added support for keyless signing. So this really helped with this problem that I talked about before, that managing a private public key infrastructure is quite complex and difficult to get right. And basically, because it's really much easier to use and reduces the complexity of implementing image signature verification, it's also now being widely adopted by the open source community and also by the Kubernetes project. So let's look at the workflows that are available for image signing. So there's obviously two, at least. One is to use command line tools, and the second is to do it in your CI/CD pipeline. Let's first look at the command line tools. So this is the simple example with the private public key pair. So as you can see, cosign even helps you to generate the private public key pairs, so you can do it from one application. And then once you have generated your key pair, you can then basically point it at any existing Docker image that is stored in the registry. And then cosign will automatically create the signature and upload the signature to the OCI registry. It will also create an entry in the record transparency log. There's some interesting things you can do around the storage of your private public key pair. So by default, it will just be stored locally on the machine where you run the command. But there's a few integrations with key management systems and even with Kubernetes. So for example, with the following command, you can write the key private public key value pair directly to a secret in a Kubernetes cluster, which is also a way of basically distributing it and making it available in your cluster for verification purposes. So this is the private public key pair signing method. Let's look at why keyless signing is such an important differences here. So as I said before, it's a complex task to manage the private public key infrastructure. And actually, if you don't do it right, it can have serious security implications through leaking keys and stuff like that. There's also the problem of how do you actually integrate this with your CI/CD pipeline, because you have some important credentials that you need to move around. You need to find a way to securely inject it into your CI/CD system. And there's also kind of not really a standard way of how you distribute the public keys so that the users of your application can use it to verify the signature. And finally, there's also the problem of key rotation. So if you have maybe your private key was leaked and you need to create a new key pair, how do you still make your old images verifiable? So really, this was really kind of like a blocker for the wide adoption of image signing. And this is why the keyless signing is an important new approach here. So let's look at a little bit closer on how it actually works. So the cosign keyless signing uses OpenID Connect identities, and it uses short-lived tokens, short-lived certificates to do the to generate the signatures. So this is an important differences, right? This is a big value add because now you can tie an image signature directly to a person potentially or to an organization, to an identity, whereas before you only knew a public that this signature was created, was signed by a certain public certificate, but not directly tied to an identity. So that's quite good. It works out of the box with many public identity providers that are running open OIDC services like Google, Microsoft, and GitHub. So you can use it out of the box when you have a user account there. Obviously, it also works with any other OIDC provider. So if you have like a Keycloak server or something like that, you can also use that. And the Sigstore project actually runs free public services. So it runs, they run their own public free infrastructure with all the components, all the services that are involved in this keyless signing. So you can use it without installing anything and just get started. Obviously, for like enterprise usage or usage in your own IT organizations, you can run private versions of these or private instances of these different components. So this is kind of a picture showing the flow of how keyless signing works. So the first step is always to establish the user identity. This is done via an OIDC workflow. So when you run cosign, then the first thing it will basically initiate an OIDC workflow where you log into, for example, GitHub, and then get an identity back. Using this identity, cosign, then first of all, it creates a certificate request or a key value pair, and it sends that to a service called Fulcure, or Fulcure, I don't know how exactly you pronounce it. And Fulcure then verifies the user identity, and it gives back a code signing certificate. And with this code signing certificate, this is only valid for a few minutes. So that's the short-lived nature of it. And this is then used by the cosign command to actually create the signature. Once the signature is created, it's uploaded to two locations. So one is the OCI image registry, and the second location is the record transparency log to have this kind of audit possibility for all the signing events. So that's kind of the process. It's really neat. You don't need to manage any keys anymore, and you can you can use a user identity to initiate the signing process. And the person that looks at the signature will also see the user identity that is mapped to the signature. So to do keyless signing, again on the command line, you really just leave out the private public key part. And this again, like I said, starts an OIDC authentication flow where you log into your OIDC provider. Now for the verification, you need to know two things. So the first thing is you need to know the OIDC issuer or the OIDC provider that was used or that provided the identity for the signature. And obviously this is how you also then kind of establish trust, right? You should only use an OIDC issuer that you trust. And the second thing is to know the identity of the person signing the image. Typically that's an email address, but it could also be something different depending on the OIDC provider. And this is how you then verify the signature of an image. So running this on the command line is nice to get started, but it lacks, of course, any means of automation. So what we really want to do is we want to integrate this in our CI/CD pipeline. One example, I just give one example here, which is integrating this in the GitHub Actions workflow. This is made quite easy because the Sigstore project actually maintains a GitHub action that you can use in your GitHub workflow, and that makes this quite easy. So let's just have a quick look at the steps to do it. So first of all, this Cosign integration, it supports, of course, all the different means of signing. So you can, if you want to use private public key pairs, you can upload your keys to GitHub and then store them as credentials and have them injected into the workflow and use them. But obviously what's quite nicer is if you don't have to maintain these keys and use the keyless version. For this, GitHub Actions has their own OIDC service. And in order to use that, you need to update your GitHub workflow with the permission to use the identity service. That's what's here. The second step is just to install the cosign action. So add that to your workflow. And then the final step is doing the normal Docker image build or container image build, container image push. And then in the final step, run the command to sign the image. So that's basically what it is. If you want to have a look at the whole workflow, I have uploaded an example GitHub repository. If you want to check this out, you can scan the QR code or use the URL. This has basically the whole workflow to release a container image from a Golang application and sign the release, sign the image. So now the other part. How do you do the verification? Let's just look at the time. So command line, very easy, cosign verify, and then the image name. Obviously drawback, no automation. Second possibility is you can do image signature verification at the container runtime level. That's an interesting idea. So one example is if you're using Cryo as a container runtime, Cryo has support for a policy config where you can basically specify which certificate authorities you trust for signatures and define some policy for verification and use that. The drawback, I would say, is that obviously it's a node level configuration. So if we're talking about a Kubernetes cluster, you have to do this configuration for every node. And it's kind of static, right? So because you have to restart Cryo when you change it and stuff like that. And also it's currently only supported by Cryo. So if you use ContainerD, for example, as a container runtime, you cannot use it. So that brings us to the final possibility and probably the canonical way of doing it, which is using Kubernetes admission control. Here's just a few examples of admission controller that support image signature verification. OPI Gatekeeper, Kyverno, KubeVirt, NeuVector, they all have kind of first-class support for implementing that. And of course, the big advantage here is, first of all, you can have different scopes. So you can have different policies depending on the namespace or cluster-wide. And the whole configuration of your image verification policies can be managed as Kubernetes resources and not as static configuration file on the node. So just to remind the Kubernetes admission call, this is like a standard interface in Kubernetes. And basically it allows us to implement arbitrary checks of all the API calls that users are doing or services are doing against the Kubernetes API. And this is a great way to also check, of course, images and check that an image has a valid signature. Because part of this flow is after the inspection of the API request, the component that implements admission control can deny the request. So when the image verification fails, it can deny the request, and then the user gets an error from the API server. And of course, the big advantage here is most of these admission controllers, they use custom resources to define policies. And that means we have a standard way to configure also the policies for image verification. This is just an example here for Kyverno. It's also on the GitHub repository. of defining a policy here for checking my image in this GitHub repository. And a second possibility is using NeuVector. So NeuVector is a bit more than just an admission controller. It's a full lifecycle container security solution. It's free open source to use. And admission control is just one component of NeuVector. So NeuVector provides a lot of feature around scanning for vulnerabilities, scanning for compliances, and also implementing a runtime security scanning. It's quite easy to deploy and configure, so there's a Helm chart to do it, and it implements many of the Kubernetes standard interfaces, so it uses admission control, CIDs for configuration, and stuff like that. This is kind of the dashboard, so obviously NeuVector can also be configured via code. So this is, again, an example of how I can verify my example image by basically providing the issuer, the GitHub action issuer, and by providing the subject, which is always the URL of the workflow. So that's one way to do it. Another way to do it is using the UI. And I just want to show you quickly how you would do that in the UI. So the first step is setting up the trust. So this means configuring the root of trust, which could be a public key, for example, or it could be a vulture service, either the public one that's run by the Sigstore project, or if you run your own instance of Reco on vulture, then you would have to provide the URL and the certificates of your private services. So that just means configuring the root of trust. And the second step is then to add a verifier. So this is when you then provide a specific user identity or a specific workflow subject that should be checked against the image signature. And then the final step is to configure a policy for image scanning, image signature verification. So this is an example policy where we want to deny the deployment of any pod that has an unverified image by adding these two criteria to it. And depending on the configuration here on the bottom, it would either create an alert if such an image is deployed, or it would be actively blocked. And then the user would see an error telling him that he violated this policy. So the report would also be immediately available in the UI. So there's a risk report log here. And if you look a bit closer, it tells us, in this case, that this image was blocked from deployment, and it also provides a reason of why it was blocked. So this was just a teaser, obviously also for you to check out this project, NeuVector. If you want to do it, it's quite easy. The Helm chart works on any certified Kubernetes distribution, whether that's managed Kubernetes, branch or OpenShift, or some other vanilla Kubernetes. Just makes it quite easy to check it out, and then you can also try it yourself with image signature verifications. So let's wrap things up with some learnings. First of all, ensuring the security of the software supply chain is becoming more and more a critical concern for all sizes of IT organizations. And container image signing verification is really part of that, and it really helps us to protect our containerized application from different supply chain threats, cyber threats. And the third learning is, while container image signing was maybe difficult in the past to actually put into practice, we now have tools and solutions that really make it much easier, and there is no excuse to not do it. And this concludes the presentation. Thank you very much.
Thank you for your presentation. I do have a question while we get the Slido slide up so that you can also ask all of your questions. But just by virtue of being here first, I can ask the first question to Jan. So you mentioned that signing should be, shouldn't be, and I quote, painfully difficult, but is ease of use enough for people to introduce signing into their systems, or do we need more?
I think the main pressure comes from the actual need to implement this as a means to secure applications, either by pressure from compliance or by realizing that there's an actual threat of supply chain cyber attacks. And the ease of use just means that there's no excuse to not do it.
All right. I like that answer, but I mean, I always think that lots of things are easy, but that doesn't mean that people do it still, even if there is a compliance issue. All right, cool. Let's see if we can get some audience questions for you. Please do ask your questions using Slido. I'm not going to walk up to you and give you the microphone. Make sure that you address your question to the right room, by the way. Like there's a drop-down little menu of all of the different rooms, so it doesn't land in a different room and they ask the speaker a question about container signing. The speaker is just like, what? Signing? What? Not all at once, though. Like you don't all need to go at once. There's nothing coming. I give you like 2 more minutes to ask your questions. So you mentioned like compliance issues. So is there any legislation that already tells companies to do container signing?
Yeah, I think that was on slide 10, maybe. Yeah, so there's a few legislation. I think I already talked about them, like the European NIS2 directive, and specifically the SALSA framework. So these are all things that tell you to implement image signing.
Right, perfect. We're getting our first question. All right, let's see. How could image signing have stopped any of the supply chain attacks that you've presented as well, right? You gave a couple of examples of recent ones where the build process was in control of the adversary.
Yeah, so interestingly, I think in none of these cases, container images were tampered or involved. So in this specific cases, it wouldn't have helped, but obviously there's analogies to how it was done, specifically with the XC backdoor, how that was introduced at some point during the software delivery pipeline, right? Because it was not really in the source code of the application until the application was compiled and packaged. So that's and there's an analogy to the container images.
Perfect. Yeah, I think the other question is just like sort of a follow-up on that, right? Like, would it have prevented the XZ package attack that you mentioned? Yeah, but like that's a similar question. All right, let's see, getting some more in there. Sorry, this is a very involved process where I first have to like approve stuff and so on. Let me see. Right, so how do you solve the challenge around trust on first use? Does keyless signing make this even harder?
I don't think it makes it harder. It makes it easier. So the root of trust for the keyless signing is the OIDC issuer, and then it's also the user identity, which is authenticated by the OIDC issuer. So if you don't trust, GitHub, Google, or something, you might trust the IDP of your IT organizations, like your Keycloak instance. So that's the root of trust. So it makes it actually easier. And with things like record transparency logs, it's transparent. You can audit who and when signed this image. You can see a lot of metadata around the image signing process. So it makes it easier and more secure.
Perfect. All right, so we have one question in here sort of twice. Let me see. Are there any other CAs than Fulcho? You also didn't know how to pronounce it, right? Naming is hard. Naming is hard and pronouncing things is harder. Supported with cosign.
No, I mean, Fulcio is a key component of Sixter cosign. So if you want to not use the public service, you would run your own version of that. The replaceable part here is the OIDC issuer, so the identity provider. That could be a key cloak. That could be an enterprise identity provider system. Yeah.
Right. How do you differentiate between forged image signatures and a legitimate one when using keyless signatures?
Well, there's the proof. The protection against the forging is the cryptographic signature that cannot be forged. So I think this is the answer to that.
Okay, we're gonna do a last one. What other tools are there besides Cosign for keyless signing, which are widely used? And if yes, are there any that you can recommend?
I think I propose two. I mean, there's still Docker Content Trust or Notary. There's also a new version of Notary, kind of maybe improved version of it called Notary 2. I don't think it has been G8 yet. So that's something that is worth looking into. Maybe that provides different or other workflow. But I think right now the open source community is kind of standardizing around Cosign.
Perfect, thank you, and thank you so much for the session. Let's do one more round of applause, and then you can all find.
Thank you.